Now, that was discrete random variables. We have two special types of continuous random variables. So the first type being the normal distribution, and then we're going to talk about a new type, which is the uniform distribution. So revisiting our normal distribution, remember our 4 P's of probability we do are the parameters, what's happening, a picture of the situation, our probability statement, and then our problem conclusion. So suppose that x is a random variable whose distribution is normal with mean 30 and standard deviation of 4. So our first P here is parameters. X is distributed normally with mu 30 and sigma 4. So as a reminder, this is our mu, this is our sigma, this means normal, and this means distributed. Okay, so that's our parameters. And which of the following is equivalent to the probability that x is greater than or equal to 26? So we're actually going to draw a picture for this situation. And as a reminder, on my picture, I always draw in the standardized normal curve because this helps me to see where the observations are and how their respective z-scores would follow. So we're going to pretend that's symmetric. Okay, I'm not going to think about it. So here, at the center of the distribution, 0 standard deviations away from the mean would give us our mean of 30. 1 standard deviation above would be 34, 2 above would be 38, and 3 above would be 42. 1 below would be 26, 2 below would be 22, and 3 below would be 18. And any observation that falls more than 3 standard deviations above or below the mean would be considered an outlier. So looking here, we are looking for what is equivalent to when the probability of some observation is greater than or equal to 26. So I'm going to draw in my line here, and I'm going to provide some shading to help me out here. Well, back to the empirical rule, we know that this is about 50%, right? 50% above, 50% below. So if I look here, I have 50% of the distribution here. And then using the empirical rule, 68% of the data happens in between 1 standard deviation, which means 34% happens on both sides. So this shaded region accounts for approximately 84% of the distribution here, which means I'm looking for which of these values would give me the same probability of happening here. So let's see, the probability that x is greater than or equal to 34. Well, I'd go over here, and by the empirical rule, that looks to be about 16%. Well, I need 84%. That's not going to work. So now let's look at 1 minus the probability that it's less than 34. So again, by the empirical rule, this would be about 1 minus 0.84. So that's also going to give us about 16% in between 26 and 34 by the empirical rule would give us approximately 68%. Less than 26, well, if this is 84%, then the less than by the complement would be about 16%. So I have a good feeling about the probability being less than 34, right? If x is less than 34, 50% happens below the 0, another 34 here. 50 plus 34 will give us approximately 84%. So it looks like answer choice A would be our would be best modeled, would have the same probability that x is greater than or equal to 26 if x is a random variable distributed normally with these parameters. So these two probabilities would be equivalent to one another, as we can see here through the empirical rule. So next up, that was just revisited there. Again, parameters, picture, probability statement. Okay, now let's look at something new called the uniform distribution. So back to our studies of Unit 1, we knew that there was a special type of symmetry in graphs, which we called uniformity. And when it's uniform, that means that all probabilities are equal. And so when I think of the uniform distribution, I normally think of a dice, right? Because we assume each number on a dice has a 1 in 6 chance of occurring. So in the same way, we're going to say that x is distributed uniformly, which we'll abbreviate as uni, with parameters a and b. Now these parameters here are going to be the endpoints. So this means x is distributed uniformly with this left-hand endpoint and this right-hand endpoint. Now what does that mean? So if we were to draw a picture here, We'll start at 0. And we'll give it some value here. Well, if I'm between A and B, whatever that interval is, and we know that each observation has an equal chance of occurring, we know that it's going to look something like this rectangle here, right? And so depending on what my partitions are, something like that. Well, since this is a probability model, we know that this area under the curve must always be 1. So in order to use the uniform model, we need to determine some of the values here. So we at least have this base here. This is a rectangle. So let's go back to our geometry days where we know the area of a rectangle, or any shape really, is the same thing as the base times the height. Well, I could find the base because in order to find the distance between A and B, I would just take the difference between B minus A. I need to figure out the height, and I know that the area under a curve must always be 1. So using literal equations here, if I wanted to solve for the height, I'm going to divide both sides by B minus A, so we obtain that the height of the model must be 1 over B minus A. So if I multiplied B minus A times 1 over B minus A, I'll always end up with the result 1. So this is what we call the uniform distribution. All probabilities are equal, and they are distributed between the left-hand endpoint and the right-hand endpoint, which we call A and B. And the height must be 1 over B minus A, so that we can preserve this property here where the area, the sum of the probabilities, must always equal to 1. So this is how we're going to use the uniform distribution. So let's take a look at this example. And if you're not clear on where this derivation is coming from, it is totally fine. This is not explicitly assessed on the AP exam, but sometimes it does show up in the multiple choice questions, and it is helpful to know when speaking about continuous random variables. So suppose W is uniformly distributed between 9 and 19. Well, remember our 4 P's of probability. This will always help us when we approach these problems. So our first P is that we look at the parameters. And so here for our parameters, we know that W is uniformly distributed between 9 and 19. Well, what does that really mean? Let's take a look at a picture here. So in order to find the height, right, I want 1 over B minus A, so this will give me 1/10. So my height of this model should be 1/10. And I'll put in the scale. Here's 0. We'll assume 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So between 9 and 19, each observation, each interval, has a 1/10 chance of occurring. But specifically here, I'm looking at the probability that W is between 13 and 17. And you can put inclusion signs here, because if it's in between there, they've got to be in the interval. This is a continuous random variable, so whether I do or do not put them in, eventually they will be included. So we're looking at 9, 10, 11, 12, 13, up to 17, 14, 15, 16, 17. So I'm going to shade this area here because I want between 13 and 17. Okay, so I did my parameters, I did my picture, and I did my probability statement. Now we are used to now converting this to a z-score, but I don't really have a mean or a standard deviation that I can do here. So we're just going to use the good old area trick. So we know that the area here, which will represent this small shape, is the small square, not square, I don't know what that is, rectangle we'll call it. The area is always equal to the product of the base times the height. So here in this problem, our base would be the difference between 17 and 13 times the height of the model, which is 1/10. So when we do this, we get that the area is equal to 4 times 1/10. So the area is equal to 4/10, or 2/5, or 0.40. But any one of these three outputs is accepted. So again, parameters, what's happening, picture, what does it look like, and then our probability statements to obtain our value here of the uniform distribution.